please to have extension now, or here's a second topic.
Okay, thanks. Yeah, so my plan is to start by talking a bit about the algebraic geometry questions that we're interested in, and then to again start introducing some of the metric techniques, kind of in a more global point of view. Okay, so algebraically, so I'm going to fix x to be a smooth projective variety over C. And then I will always write this, so this will be kind of the main object, the canonical bundle. Okay, so this is you take the cotangent bundle of x, and then you take the top wedge power of that line bundle. Okay, the reason we're interested in the cotangent bundle from the algebraic geometry point of view is because this is basically the only line bundle that we have on an abstract variety. Right? If I look at the sections of the canonical bundle and its powers, they give me the main kind of birational invariants that I have to, when I'm interested in x up to birational equivalence. So I get these birational invariants. So on the one hand, I could look at the spaces of sections. So I take the canonical bundle, I raise it to some power, and then I look at the space of global sections. Then on the other hand, I could just talk about the numbers. So I just look at the dimensions of these spaces. Okay, so this is called the nth plurigenus. Okay, so essentially we're interested in the behavior of these kind of quantities. Okay, so let me mention first of all, just kind of in passing, there's a very important theorem related to these spaces, which is that if you take all of these spaces together, you can actually build a kind of canonical geometric object out of them. Right? So there's this famous theorem due to Berker, Caccini, Haken, and Kernan, which says that if you take the direct sum of all of these spaces for m from 0 to infinity, then, well, so for m equals 0, you just get the complex numbers. And then for the higher ones, you can obviously multiply it, right? So this is actually a graded ring, because you can multiply sections and, again, sections of some section of some higher power. And the famous theorem is that this is finitely generated as a C algebra. So this is the so-called canonical ring. So. And the use of that you can make is that, so since I have this graded ring, I can look at, I can do this construction called the Proj construction, where you just make a projective variety out of it, so that this becomes the homogeneous coordinate ring, basically. And this variety is just canonically associated to x, right? You don't need to start from any projective embedding, you can always make this thing. And the dimension of this thing, this is called the Kodaira dimension. So this is the so-called canonical model. So this is some projective variety, typically singular, that you build out of the sections of the canonical model and its powers. And the Kodaira dimension is the dimension of this thing. So this is one definition, right? So this is this is called kappa of x. This is simply the dimension of this. Or minus infinity if there are no sections, or if this thing is empty. Right? One possibility is that for m greater or equal to 1, there aren't actually any sections of the canonical bundle and its powers, in which case this algebra would just be C, in which case the Proj would be empty, I guess. In that case, we just, by convention, we set the number as minus infinity. Okay. So this is the most conceptual definition of what the Kodaira dimension is. It's also the most complicated one, right? Because you need to use this finite generation of this ring and so on. So I mean, there's a more elementary definition of it also. But conceptually, that's what it is. So for example, what this will do is, in the case when the variety is of so-called general type, so when this Kodaira dimension is equal to the dimension, then you get something which is actually birational to the original variety X. And so then you get this canonical model, this canonical projective variety, which is birational to your initial thing. But it's kind of a distinguished representative of the birational class. Yeah. Okay, so I was going to say the numerical, if you just want to calculate it in terms of the numbers, just because of the way you compute the dimension of a projective variety from the coordinate ring, you can see that the Kodaira dimension is actually, you look at the log of how these plurigenera grow, you divide it by log m, and then you take the lim suit as m goes to infinity. So this is in terms of the numbers, right? This is just the dimension of this kind of variety. So again, this can be, it can be minus infinity if these are all 0, and then otherwise it could be go up until the dimension of x.
Okay. Basically, you're saying that the dimension is like n to the kappa.
Yeah, that's right. So then, so what this is saying is that, that these PMs, these plurigenera, they're going to grow with m as a constant times m to the kappa of x. So for example, when it's of general type, meaning when the canonical bundle has lots and lots of section, then you're in this case where it grows like dimension of x. Okay, so this quantity. So in some sense, this kappa of x behaves a little bit like a dimension, because it is a dimension of this thing. And the interesting questions are somewhat to what extent does it behave like usual dimension in geometry. And there's a famous conjecture about this Kodaira dimension called the Itaka Conjecture. So this is kind of the main algebraic geometric thing that we're interested in. So the Itaka Conjecture what this does is it predicts how this Kodaira dimension behaves when you have a family of varieties, so when you have a map between two varieties. Okay, so this. So more precisely, the kind of maps that it's about is so-called fiber spaces. So it's maps of connected fibers. Okay. So let's say that I have a fiber space of this type. So I have a morphism from a smooth projective variety to another smooth projective variety. So let's say it's an algebraic fiber space. So I'm just going to make a very restricted definition of that. So by algebraic fiber space, I will mean that x and y are smooth projective. The map is surjective, so that the base really parameterizes things and not a subset of the base. And then I want all the fibers to be connected. So it's a nice family of connected fibers. Connected fibers, I would say algebraically by saying that the push forward of the structure sheaf is the structure sheaf. Right? Okay, so then this family is going to have like a general fiber, if you like a typical fiber. So let's say F is the general fiber. Fiber was some general point. And then Itaka's conjecture predicts that if you know the Kodaira dimension of the base and the Kodaira dimension of this fiber, you can say something about the Kodaira dimension of the total space. So what it's claiming is that the Kodaira dimension of X is always at least the Kodaira dimension of the fiber plus the Kodaira dimension of the base. Okay, so you see that, so this kind of statement, this is trying to make a precise version of like some general principle, which is if you have varieties with small Kodaira dimension, they cannot map easily to varieties with bigger Kodaira dimension. Right? This kind of thing will say, for example, if kappa of x is small, then it forces kappa of f and kappa of y both to be small. There's one kind of special case where this is just vacuous, or kind of by definition, which is the case where things have Kodaira dimension minus infinity. So for example, if kappa of y is minus infinity, then this inequality is declared to be true by default, right? Because the right hand side is minus infinity. So for example, a variety kappa with kappa equals minus infinity is something like P1. Conjecturally, anything that's covered by rational curves. That's something like P1, right? If I take y to be P1, actually, there cannot possibly you cannot get any information about x. Because if you think about it, any variety x, up to by rational modification, you can map it to P1. Right? You embed it into some projective space, take some hypersurface sections of really, really big degree, and take a general pencil. That will give you, after blowing up the base locus, that will give you a map to P1. The fibers can be of general type if you want, if you make the degree really big. So any x can map to P1 with fibers of general type. So in that case, you cannot say anything about Kodaira dimension x. Okay, you're going to ask questions if you have questions, right? So if I, yeah? Okay. So now I will tell you now what the basics, yes?
Is the Kodaira dimension of the fibers constant for general fibers?
Yeah, for the general fiber it's constant, yes. Okay, so I will tell you now what's the kind of strategy for proving this. So this strategy is just a philosophical strategy, it doesn't actually work for proving it, but it will kind of explain why we do the kind of metric things that we do. Okay? So the strategy in quotes is very simple. So it consists in realizing that the canonical bundle upstairs can be written as the pullback of the canonical bundle from downstairs times the relative canonical bundle. And so then if I want to calculate the space of sections of omega x upstairs, I can calculate this by first pushing it down to y. And then I can use the projection formula to write this as write this in this form. Okay? And so then the idea is to try and study this guy, this push forward of the relative canonical bundle. Get some information about that. Okay? Okay, so there's some things that we can say easily. So this is a torsion-free coherent sheaf, I guess, on the base. It's not necessarily locally free, but it's just a torsion-free sheaf. It is locally free at the places where the map is smooth. So at smooth points, at points y where the morphism f is smooth, the fiber of this guy is actually just, the y is just the space of pluricanonical forms of the fiber. And this is a consequence of this famous deformation of invariance of plurigenera, so of series invariance of plurigenera. Okay, so that, in fact, this thing is actually locally free over the smooth locus of the map, and the fibers are just the pluricanonical forms of the fibers. Okay, so in particular, the rank of this thing, the generic rank of this thing, is exactly this number Pm of f, of the generic fiber, right? So the rank, the generic rank is okay, so now, so let me show you now how we prove Itaka's conjecture, right? Under some assumption, which is never true in practice. But anyway, that's all. So this is a very unrealistic case, but let's assume that we happen to know somehow that this guy here was globally generated. Okay, so that the global sections generate this sheaf at every point. Okay, if this was true, then what I could do is I just go to a general point. The fiber is a vector space of rank Pm of f. I just take a basis for that vector space, just extend it to global sections. So what this will give me is, it'll give me an injection from this space times Oy into this sheaf. Right, again, I go to a general point where the fiber is f, I pick a basis for the sections, I pick a basis for that fiber and extend it to global sections using the global generation. And then I'll get this injective map of sheaves. So then tensor by omega y to the m, you'll get an injection like this. I tensor with omega y here and again using the projection formula. And then if I take global sections, I will get this inclusion here. Okay, do you see that then now what this says numerically is that Pm of f times Pm of y is less or equal to Pm of x. And so if I take logs and divide by log m and take the limit, then I get exactly the inequality that I want. Okay? So unfortunately, this never works in practice because this guy is never going to be globally generated. But what it says is, nevertheless, what we should try to do is look for some kind of positivity with this sheaf. If you have some kind of information that this is in some sense positive or semi-positive, you might try to make some argument like this. That's kind of the question. Okay, so now so I'm going to divide this into old and new results. So the old results, I just say very briefly. So there's some older results which talk about positivity. And what they showed is, without going into the careful definitions, that this thing has something called weak positivity, a property called weak positivity, which, roughly speaking, means that if you tensor by a little bit of an ample bundle, then it becomes, it's not too far away from being globally generated. So maybe let me put some names here. So this goes back to Fujita, Kawamata, Kola, and Friedrich. So what they showed is that this guy here is always ET positive. Again, it won't matter too much for us what this is because this metric approach is going to give like a more quantitative version of this weak positivity. But anyway, so what they could do with this is they could prove, so this was enough to get Itaka's conjecture when f or y, so either the fiber or the base, are of general type. Okay? So if there's enough positivity either in the canonical bundle of the fiber or the canonical bundle of the base, then positivity is good enough to overcome this weak thing here. And then something like this argument is going to go through. Up to some error terms, let's say. So the new results, the things that we want to talk about today are, this will be mostly explained in Mihai's talks in the afternoon. The newer results are to put this in metric terms. So the upshot of the newer results is that we'll show that this sheaf is positive in the sense that it has a singular metric. It has a metric with certain kind of singularities, which runs into the issue that Brook kind of raised at the end of his talk, namely how do you define metrics with singularities and things of higher rank. And this singular metric is positively curved, which is, I guess, it's semi-positively curved. So I will define them later. Okay, so this will be sort of the kind of positivity that you can get from these sheaves. And then in certain cases that are more general than this setting, it turns out that this metric information is good enough to again prove Itaka's conjecture. So again, Mihai is going to mention the most important new case, which is the case when y is an abelian variety. So. Or when the dimension of y is opposed to. So this is the plan. Okay, so any questions at this point? All right, so now I thought we kind of divided up the work a little bit. I will try to start explaining this kind of metric approach, so what's involved in that. I give some basic definitions and try to start explaining why there are these metrics and what this means. So you can see that there's going to be some technical issues, right? Because this f lower star omega x over y to the m, it isn't even a vector bundle, it's only generically a vector bundle. So the sheaf itself has some singularities, and then on that we want to put a metric that has some singularities, and so on. It needs a little bit of work. Okay, so let me start talking about this kind of construction in what you might call the absolute case. So by the absolute case, I mean that I just have a smooth projective variety, and I don't have a map. So just x is smooth projective, and if you want, if you're kind of functorially minded, then I'm thinking of the case where x just maps to a point. What's my goal in that case? So I want to explain why there's a metric on this push forward, right? This push forward in the case when the mapping to a point is just the space of global sections of omega x. So my goal is to explain why there is an inner product, a nice inner product on this space. When n is at least 1. This is basically what the thing is saying in that case, right? There isn't any statement about curvature because it's just over a point. But anyway, that's the first issue, like how do you get these inner products? And then later, when I talk about the relative case, where you have a family, and then we'll be interested in how these inner products vary from one point to another, and then we have to talk about the curvature and so on. Okay, so let's start with the easy case. So the easy case when m is equal to 1, right? So m is equal to 1, I'm looking at, this is just as warm up, I guess, just the space of sections of the canonical bundle. So in that case, I'm going to think of this as being the space of n0 forms on X, where n is the dimension of X. And then there's an obvious thing that you can do is if you have an n0 form, you can make an inner product by just, well, you have two of these, you conjugate one of them, you get a 0n form, then you wedge them together, you get an nn form, and then you can integrate. So if I'm given maybe v and w in there, what I can do is I can define their inner product to we just basically integrate over x. I'm just going to write it like this. Yeah, right.
You just mean that you take a constant and make that positive?
Yeah, I just mean I make it positive. So I will write it in local coordinates. So what I mean by this is that locally, v is going to be some function dz1, dzn. W is going to be some other function in local coordinates. So if I take v wedge w, it's going to be f times g bar times this times the conjugate of that. And then I just need to permute the dz's until it actually becomes the volume form. And I need to multiply by some power of I. Right, so what I mean by this notation, this integrand is just actually, in these local coordinates, it's just f times g bar times the volume form in C. And if you integrate that, then you get this.
It offends the analyst to see the absolute value there.
Yeah, I mean, if you like it, okay, if the analyst is offended, then
That's the sensibility.
I don't know, I don't want to offend you, so. So you multiply by this constant. Okay, so this is the constant that the -1 is how the permutations that you have to do to get it into the correct ordering, and then the 2 is because dz bar is like 2 times the volume form. Okay. Now the tricky case is when m is bigger or equal to 2, right? When m is bigger or equal to 2, I can't do this. But still the claim is that there is always a canonical inner product on this space, even when m is bigger or equal to 2. Okay, so let's do this in some steps. So the first step is, well, I can still do something like that. It doesn't give me an inner product, right? So I can still, if I have some, can I give some name to this? Let me call this Vm. So this will not depend on m. So if I have some m canonical form like this, still locally, I can write it as I can write it in this form, right, in local coordinates. Now it's just an nth power of this thing, because it's a section of omega x dm. So I can still do, I guess the analyst will be offended. So I'm going to write it like, I'm going to write it like this. So HB bar maybe. Let me write it as b to the 2 over m. Okay, what I can still do is, basically I wedge it with its conjugate, so I get an f absolute value f squared, and then I just extract the mth root out of it to just make a volume form, right? So this y by square over m. So this is just, by this I just mean that you do this kind of thing. And again, if you think about it, if you change coordinates, then the f and the z's will transform in such a way that this thing will actually not depend on the coordinates. And so then I can still integrate this quantity over x. And this is, I will call this quantity L of v. So this will be the length of v. And I guess I want to raise this whole thing to the m over 2 power to make it kind of linear. Okay, so what do we see about this? So it's still positive definite in the sense that the length is 0 if I know that v is 0. Because I'm still just integrated some power of the absolute value. This is also linear in the sense that a constant will come out like this. But it won't be, in general, it won't be a norm. It's not a norm. So the problem is because of this 2 over m power, it doesn't actually satisfy the triangle power. Okay, but I still have more than just, I have more information than just on a random vector space, right? I have a way to measure the lengths of things.
It's okay if m is 2, by the way. Just not what's
Yeah, no, I guess you're right. Okay, and so now the next step is, we can now do an intermediate thing. The fact that we have this length function means we can now put some extra structure on omega x. So what we can do is we can build a singular metric on the line bundle omega x. So in the way that Brook talked about, right? This is a holomorphic line bundle. We're going to make a metric on this line bundle, which is going to be singular at certain places. Usually the way you would do this is, well, what I have here is the space of global sections of this mth power. Right? Anytime I have a bunch of global sections of a line bundle, I can use the construction that Brook explained, just put some metric on it by just choose a local trivialization, write these things as multiples, and then do this 1 over the sum of the squares of the equations. The problem is that in general, that construction will depend on which basis I choose in the vector space. But in this case, since I have this length function, I can get rid of that, and I can actually make a canonical choice. So the idea is like, so this is using this L. So the idea is like this. So I'll just tell you what the metric is. Here. So I have some point at x, and then I have some vector that I'll call C, in the fiber of the canonical bundle at x. And I'm just going to define the square of this thing with respect to this metric. So this metric I'll call HM. So I'm going to do it like this. So this C is a vector in the fiber of this thing. If I raise it to the mth power, I get a vector in the fiber of omega x to the m. And then among all the global sections of omega x to the m, I look at all the ones that take that value at that point, and then I look at the shortest one. And that gives me a way to assign a number to this vector. Right? So what I'll do is I'll take the length of v, where v runs over all sections of omega x to the m, such that at that point, the value is the mth power of this. And then I'm going to take the infimum over all of these guys. And I guess here again, to make it match with the orders, because I'm raising to the mth power here, I should do a 2 over m power here. So that it becomes, it has the correct linearity properties. Right? Because v is c to the m, so I need to divide by m in the exponent. And then because I put a square here, I put a square here. So let's look for the shortest m canonical form. Given. So what's going to happen is this thing will be nice most places, but if you're at a point in the base locus of this VM where every section of omega x to the m vanishes, then of course you won't be able to find such a V. And so at such places this thing will be infinite. So this will be plus infinity at x in the base locus. Where all the sections of VM vanish. then there's a useful lemma that one can prove is, so this metric, as I'm defining it pointwise, this is actually a singular metric in the sense that Lore defined it, and moreover the curvature is non-negative. So this HM is a semi-positively curved so again, I'll just tell you sort of the punchline maybe in one line. So again, locally, on some open set, I'm going to trivialize the canonical bundle by using local coordinates, like this. And then I can write any section in this VM. Locally, I can write it as some holomorphic function times this guy to the nth power. Okay? And then I want to express, I want to calculate what the norm is of this section here. Let me call this S. So when I calculate with respect to this HM, the pointwise norm, and I'm going to write this again in the usual way as like e to the minus phi. Maybe I'll put an m here. Okay, now the idea is that how do I get forms like this? So if I'm in these coordinates, what I need to do is I can just take any v like this. I divide it by the value of this function gv at the point x, and I'll get something that goes with it on the right hand side here. And then you can just stick in that expression and kind of rewrite this definition. And then what you end up with after a little bit of calculation is you'll get that this function phi m at the point x, it comes out to be the supremum of these quantities here. So it's 1 over m, the log of these holomorphic functions, squared, and you take the supremum over all v such that L of v is less than 1. Okay, so that's what happens when you stick in the right forms there and then rewrite it. Okay, so then the point is that since the g's are holomorphic functions, the log of the norm squared of g, these are all plurisubharmonic. Right, so these functions are they're plurisubharmonic functions. And then I'm taking the supremum of the family of plurisubharmonic functions. So then again, that and the fact that I have this bound here on the length, that actually implies that this VM is again plurisubharmonic. So this is.
So I guess the third crucial property, the submean value property, there's this
So again, there's a little argument here. So if the fact that I'm bounding this L of v, this says, so this condition here says in particular that the integrals of these functions are bounded, like independently of v. And then, like Dora explained, once I have a bound on some integral of the holomorphic function, I get an actual bound on the pointwise size of the function, and so I get some kind of uniformity that makes this supremum behave more nicely than management. Alright, so that's the second step, right? And so now the third step is, now we write omega x to the m as omega x times L, where L is omega x to the m minus 1 with the induced method. And therefore, my space here is actually the space of just omega sections of omega x times L, where L is this line bundle with this semi-positively curved metric. And now the thing is, in general, if I'm in this kind of setting here, I have canonical bundle twisted by some line bundle, and the line bundle has a metric. On this kind of space, I always get an inner product. So in general, on namely, again, what I can do is if I have two sections, maybe let's call them V and W again, I can define their inner product. Again, like this. I'm just going to write it in a slightly awkward way. So I'll do V when W bar. So that again is an NN form. And now it has coefficients in L and L bar. And then I evaluate the coefficients by using my metric H. So I'm going to write this like this. And then I get, again, something that I can integrate. Okay, so again, locally, V would be some function times dz1, dzn, tensor some local trivialization of L. W would be some other function, dc1, which dzn times S0. And then this quantity that I'm integrating is just f g bar e to the minus phi times the volume form. Where so phi is the local weight for the metric. So the metric on this line bundle is this e to the minus phi. Maybe let's call this phi L. Okay, and so then you get it. Okay. Except, well, you don't actually literally get an inner product, right? Because the thing, you get something that you can integrate, but the problem is it might be infinite, right? Because the thing, if the metric is, if this phi is singular, then this interval might actually not be finite. So more precisely, if I look at, for example, the inner product of V itself, so this will be again the integral over x. Here I'm so locally the integrand is and so this is finite if and only if my V is belongs to the multiplier ideal. Right, so you see that if you want this integral to be finite, I'm asking that f is in L2 with respect to this weight e to the minus phi L. And that's exactly the definition of the multiplier ideal. So this inner product that I'm defining is actually finite only on this subspace. So this is what I would call a singular. It's a singular inner product. So it's maybe I should tell you the definition. So if I have V is a vector space, finite dimensional vector space, then a singular inner product is a function from the vector space to 0 plus infinity. And that satisfies the usual axioms for an inner product, but kind of allowing infinity as a value. So such that. So this is so usual axioms for inner product. For inner product one. But it can be plus infinity. And then I look at the subspace, the finite subspace, which is those vectors for which the norm is less than plus infinity. And then on this finite subspace, I actually get an inner product. precisely, I guess I can also allow that certain vectors have not. Okay, maybe I should say this here. So what do I mean by singular, right? So if you think of a usual inner product, an inner product is some positive definite Hermitian form. Now, the way in which an inner product can become singular, there's two ways you could think about it, right? You could relax two conditions, right? On the one hand, you could relax the condition that everything has finite length. So certain vectors can be infinitely long. Another thing you could relax is the strict positivity. So you could allow that there are non-zero vectors that have zero length.
So, if it satisfies these axioms of inner products, doesn't it follow that the V infinity is also a subspace?
No, it doesn't. Because I can have an infinite vector and another infinite vector, but there's some you can cancel out. Right? V minus V, V has infinite length, minus V has infinite length, but V minus V is 0. So that kind of thing can happen, right? But the finite ones definitely are a subspace. So I guess I'll ask here that it's for a semi-positive definite. Say. Okay, so now I get another subspace, which is the set of vectors with a zero length. And then I get a well-defined inner product on the motion. Like the finite vectors modulo the vectors of length 0, and then I get an actual positive definite inner product. Right? And so you get this using polarization. So if I'm only talking about the length, the way I can recover the inner product is in this kind of way. Right, so I'm only talking about the length, so that I don't have to talk about the inner product of two infinitely long vectors, for which I cannot assign a number. But then if I look at the subspace on which stuff is actually finite, since I'm including in the conditions that this parallelogram law should hold, on that finite subspace I can use the polarization identity to recover the inner product from the long vectors. And then this is going to be positive definite once I modify this. Okay? So our typical example of this is, like I said, this situation here, right? So if I look at this functional here on the space of sections of this adjoint bundle omega x times L, I get an inner product which might be infinite, but it's finite on the subspace where I put in the multiplier. So that's the typical example. Okay, now in this special situation here, where I use this metric that we constructed using the length, one can show that every M-canonical form actually has finite inner product. So it turns out in this case that this is actually equal to the space with the multiplier you predict, because in fact one can show that the length squared of any v is actually bounded by it's actually bounded by this funny length function that we defined at the beginning. So in fact, even though this metric is singular at the base locus of the linear system, the singularities are not bad enough to make these things. The singularities are mild enough so that all the global sections actually integral. Okay, so then I really get an actual honest inner product just in this space. Yeah. So that's kind of the absolute construction. Okay, so you see that it's a little bit cumbersome. I mean, to sum it up once more, you measure the lengths of forms. You use the length measurement to put a metric on the line bundle omega x. And then you think of this omega x to the m as omega x times omega x to the m minus 1. So it involves kind of two distinct things. Like first you talk about pluricanonical forms and their lengths. And then secondly, you need to consider your pluricanonical bundle as an adjoint bundle like this. So in the general case, you also have to study these two things separately. On the one hand, you have to look at pluricanonical functions and their lengths and how that varies from place to place. And on the other hand, you need to understand bundles of this type, adjoint bundles like this, and how you deal with that, right? Okay. Other questions? Yeah.
How can the product be zero with that norm? Like, how can a vector have zero norm?
You cannot.
Okay.
Yeah. So, right. So for this specific case, this thing is the finite subspace, and the V0 is just zero. Yeah. The reason why I want to allow cases like this is, if I have inner products that can only be infinite certain places but can never be zero, if I go to the dual space and I look at the induced construction of the dual space, then it will be opposite. There will be non-zero vectors that have zero rank. Yeah. Actually, maybe I should also mention this here. So this also, you get an induced singular inner product on the dual space by just the usual kind of construction. So if I have a functional, so f is some function from U to C, the way I would define the length of that functional is I simply I look at the supremum of these evaluated in a vector over the length of the vector, and then I look at all vectors in V that and this will put me a singular product on the dual vector space. And you can check that this construction, basically it swaps the finite part to the zero part on the two sides. So the finite things will go to, the infinite things on one side will basically correspond to things that have length 0 and vice versa. All right. So now about the relative case. So now I really have a morphism, and I'm interested in the same kind of construction. So, but relatively. So again, the goal is, roughly speaking, to get a singular metric on this sheet. Okay, again, the construction is somewhat involved because you need to deal with, yes?
Alright, so what was the motivation again for defining this singular thing rather than, you define this inner product on the canonical bundle, and you showed how you could sort of extend it to these adjoint things. Why not just do that with the canonical bundle tensor itself and get things on the pluricanonical bundle that way?
You mean, so why am I talking about singular things here? Or?
Yeah, like what was the, it seemed like we were just trying to define metrics on pluricanonical bundles. Why do we want these singular ones specifically rather than just taking the one on the canonical bundle and taking its powers?
What is the one on the canonical bundle?
Well, we started off by saying that, you have an inner product by taking a top form and sort of wedging and integrating with its bar. And then if we had this thing where we had the canonical bundle tensor some line bundle L. So if that L was the canonical bundle, it seemed if we had a metric on L, we could extend it to something on.
Oh, but the first thing you mentioned is an inner product on the canonical bundle. Then you need a singular metric on the canonical bundle.
So I mean, you go from the global sections of the canonical bundle to the inner product, or to the metric on the canonical bundle, right? But you need the original space of global sections of the canonical bundle to start with.
Okay.
Because the canonical bundle by itself, it doesn't come with any kind of metric, right? Okay, yeah, so this construction here. So it's a little bit. Well, there's some technical issues that come from the fact that, as I said earlier, this thing is not locally free. So this sheaf itself has some singularities, right? So you have to kind of deal with that. So what I will talk about is just on some big open set of Y where things are nice. How do we put a metric on this thing? And then essentially the idea is that we use the construction that I gave over there, fiber by fiber. So this will give us fiber by fiber, will give us an inner product. And then we need to understand how these different inner products vary from point to point. And then we want to understand curvature, what it means to be positively curved. Okay, so maybe I should start by just giving you the definition of just what's a singular metric on a vector bundle, so on. So we'll only really deal with the vector bundles. So let's say again X is some complex manifold. E is a homomorphic vector bundle. And so then what's a singular metric? So a singular metric H on E is, and so I'm just going to define it pointwise because that's kind of how it comes up in the construction. So I'm just going to say that on every fiber of E, I have a singular inner product in the sense I talked about earlier. So it's a collection of singular inner products on the fiber. So and then I want this thing to be reasonable in two ways. So for the variation from point to point, I'm not going to ask much. I'll just put the weakest possible condition, just that it varies in a measurable way from point to point. In reality, the metrics that we'll actually look at, they will have some nice regularity. They'll be semi-continuous or something like that. But for the purposes of the definition, let's make the most general definition. Okay? So such that so for every section, for every local section, yes. So whenever I have some open set, some homomorphic section of E, I want the function x goes to this is measurable. So that's a function that assigns to every point a number between 0 and plus infinity, and I'm just asking that that's a measurable function. And so I'm going to write this function as just S. Maybe I guess I gave the name, so let's put a subscript H here. So this is a function from U to 0 plus infinity. And then the second condition that I'll ask is that at least almost everywhere the thing is nice. So in this metric, there can be many points where it is either infinite or not positive definite or whatever, but I want at least a set, I want that random stuff to happen on a set of measure 0. So for almost every x, meaning except on a set of measure 0, my inner product here is an honest inner product. Okay, meaning finite, and the only vector of length 0 is this other vector. Okay, now if I have this, I can also dualize. So by this construction over here, on every fiber of the bundle, I have a singular inner product. By applying this construction fiber by fiber, I get a singular inner product in the dual of that fiber. And again, since my definition is so weak, it's not hard to check that these things again fit together into a singular metric of the dual bundle. So if I dualize fiber by fiber, I get an induced singular metric on then I'll call H star on the dual bundle. Okay. And then, now here's the, so I mean, again, we're not really asking for very much, right? I mean, I'm just saying that we have a measurably varying family of singular products, basically. It's an extremely weak condition. Now, the crucial definition is to be able to say what it means for such a metric to have positive curvature. And like Draw mentioned, we're not actually going to do this by defining the curvature tensor and then saying the curvature tensor is positive. The problem is that there's examples that show that once you go to beyond line bundles to things of rank 2 or bigger, there isn't actually a well-defined notion of curvature tensor. Even in the sense of distributions or whatever, you cannot actually define a curvature tensor. Because of the problems that Draw mentioned, like you cannot multiply distributions, and in the formula for the curvature tensor, you're supposed to multiply stuff. So instead, we're just going to define directly what it means to be. So I'm going to have a bundle and then a singular metric like this, and we'll say that this is semi-positively curved. And then I'll just tell you what the condition is. So for every local section of the dual bundle, if I calculate the pointwise length of the section of the dual bundle, and then I take the log of that, then I get a function which is pretty simple. The function log. Maybe we can put the square, maybe just for fun. This pure simple one. Okay, that's the definition. Now the reason for making this definition is, in the case when you have a vector bundle with a smooth Hermitian metric in the usual sense, like a smooth metric like a differential geometry, then one can show that a smooth metric has non-negative curvature tensor in the sense of Griffiths, or in the kind of weakest possible sense, if and only if this thing happens. Every section of the dual bundle, the log of that to the second one, right? So for smooth metrics, this is equivalent to curvature tensor being non-negative. So, but then the advantage of making this definition is that we can say curvature without mentioning the curvature tensor. They have to.
Maybe you said it, but I was focusing on something else. But it's a little tricky. So when you say the curvature is non-negative,
Yeah,
it's
so
in the weakest possible
Yeah.
sense.
So it's in Griffith's sense, so it's the weakest sense. So I mean, so what it means is like anytime you take a tangent vector on the base, you stick in the tangent vector and its conjugate, then you get a matrix, and you want that matrix to be semi-positive definite. Okay, if you're an algebraic geometer, there's a different way to think about this. I'll just mention. So sections of the dual bundle are the same thing as maps from E to the structure sheet, right? More generally, you could consider maps from E to line bundles. And this condition here is actually equivalent to just saying that anytime I have a line bundle quotient of E, and I put the induced metric on this line bundle quotient, then on that line bundle, the metric is actually semi-positive in the sense that Draw expected. So it's a definition in terms of rank 1 quotients of E. You ask that every rank 1 quotient has positive curvature. Okay, so this is a little calculation. Right. Good, so now let me get back to this slide here. put this singular metric. So at least let me explain a little bit how to get started on this. So we'll do this. Let's do this in the case when just over a nice open subset. Okay, so this nice open subset, I'm going to choose it in such a way that basically everything behaves well. So I want f to be smooth over y0, so I don't have to deal with singularities in the fibers. Then I want this, let me call this script f, this sheaf. I want the script f to be locally free. And also I want like some base change property. So, no, sorry. I actually said it wrong. I'm not going to do this one, sorry. I'm just going to do this case. So I push forward. So I have on L, on X, I have some line bundle with metric on X. And I'm going to push forward the canonical bundle times that line bundle times this metric, times the multiplier addition. Sorry. I'm just going to talk about this case. Yes. The relative canonical. Yes. Okay, and then the way you deal with the push forward of omega x over y to the m is like in the other construction. So first, you put a metric on omega x over y upstairs, and then you think of omega x over y to the m as omega x over y times omega x over y to the m minus 1. And you deal with it as a special case of this more general setup. Okay. So still for this guy, I'm going to pick a nice open subset like this. F is nice. And also I want the space of, I want the fiber of this F, the fiber at the point, to actually be a subspace of the okay, so xy will always be the fiber over a point, and then ly, hy will be the restriction to the fiber. Okay, so I also want to have base change in the sense that the fibers of my bundle here are actually subspaces of the space of sections of the fiber. And again, this is going to happen over some open set on the base. This is actually going to hold. Okay, now basically, so here again, I'm going to assume that this thing has non-negative curvature, which I'll write like this. So then we already know how to get a singular inner product in this space. Right? On each fiber, it's just canonical bundle times a line bundle. I have a metric on the line bundle, so I know how to put an inner product in this. So in particular, it's going to induce for me an inner product in this thing. So maybe, again, let me write f restricted to this thing. Since this is actually locally free, I'll just write it as a vector bundle E, and then I'll just call this EY, the fiber of the bundle. So the first observation is that I have a bit of information about this EY. So this is where I start using Osawa-Takimoshi. So the Osawa-Takimoshi theorem will tell me that if I look at sections on the fiber that are in the multiply ideal, so sections that are square integral on the fiber, this is a certain subspace of this space here. That's always contained in this EY. Okay, so this is what this will say. Right, because Osawa-Takimoshi says, if I have a section of omega times L on the fiber, if that section has finite L2 norm, then it extends to a neighborhood. And the sections, if you think about it, EY, since EY is defined as the push forward, those are exactly the sections that extend. Right? So the fact that I have extension, Osawa-Takimoshi says, this EY at least always contains this subspace. so now maybe this is step 2. So on this H naught, we have a singular inner product. From the fact that I have the metric on the line bundle. And so this will induce one on this subspace. So maybe I'll call this, and I need to put some notation for it, so maybe I'll call this with an uppercase H. Something like this. Okay, so I'll use this uppercase H notation. So I mean, so I do have a family on every fiber of my bundle. I have a singular inner product, right? And I know where it's finite. I know it's finite exactly on this subspace here. Okay, so then the third step is to observe that these inner products, they actually form a singular metric in the sense that I define. So this gives a singular metric H on this vector bundle in the sense that I defined, right? So again, there were two things that we have to check for that. One thing is we have to check that if I take any section, then the pointwise norms, they give me a measurable function. But that's pretty easy, because that's in fact just more or less like a C infinity argument, right? So because I'm assuming that the map is smooth, locally C infinity, it's a product of the fiber times an open set in the base, and then I just use Fubini's theorem to just integrate over the fiber. And then similarly, by some Fubini theorem argument, one can actually show that at almost every point, the sections have to have finite length. And so that this inclusion here is actually an equality for almost every point. And so that outside of the set of measure, zero things actually good. Okay. And so then, really the main thing now is to show that this metric actually has a positive curvature. Right? So then the main theorem that one wants to prove is that, so given like a fiber space, and then LH and X, the singular metric H on this E, which is my F restricted to this nice open set, this is semi-positively curved. Okay, so this is the main result of the multiple. So again, maybe for every local section of the dual bundle, the function is pluricanonical. So that is the thing that we'll have to do. Now it looks like I do not want to be able to prove it. So the thing that one does for this is you make heavy use of the Osawa-Takigoshi theorem. So what the Osawa-Takigoshi theorem does is it gives you this ability to extend sections of a fiber to nearby fibers, right? And the fact that you have this extension, right? Okay. So so what's the problem, right? The problem with studying this function is that the norm on the dual bundle is defined pointwise by taking a supremum pointwise. It's the norm of a functional computed pointwise. So a priori, it could be that at every different point, I need a different vector in the fiber to compute the norm of that functional, and I don't have any control over how it moves. The Osawa-Takigoshi theorem will make sure that as I move from one fiber to another, things are sufficiently uniform so that I can control the behavior of this function. And then the other thing, which unfortunately I have to defer to Mihai for, is for this plurisubharmonicity, one has to show some mean value inequality. This mean value inequality, for that, you really need Osawa-Takigoshi with a pi, with a specific value of the constant. Okay, sorry, I think I need to stop, so thank you.